Hello again, everybody, and welcome back. This is part B of example 5.5, and we're in forces and Newton's laws. And we just got done figuring out in part A what the acceleration of each canoe was right here. So for an equal and opposite force being applied between the two canoes, it looks like this guy is doing the pushing right there, but still the same force is being applied in two different directions. For that force accelerating this canoe, it's going to result accelerating this mass, I should say, this greater mass, it's going to result in a lesser acceleration. For the same force accelerating this canoe with less mass, it's going to result in a greater acceleration. So part B is asking, what is the separation of the canoes after 1.2 seconds of pushing? All right, so here's where we need to take our knowledge about the net force. So we should say the net force on 1. Net force on canoe 1 equals the mass of canoe 1 times the acceleration of canoe 1. All right, and net force on 2, net force on 2 equals the mass of 2 times the acceleration of canoe 2 right here. Well, what's this asking us about? This separation. Well, that's a displacement. All right, so in which of these values is displacement? Is displacement a force? Is it a mass? No, it's an acceleration, right? It's in the acceleration. It's in the, you might say, the equations that deal with acceleration. So what we're going to do is we're going to say, okay, well, we have these accelerations right here, here, and here. Let's see if we can determine a total separation between the two canoes. All right, so I'm actually going to go back and delete that. So we can say for canoe 1, the initial velocity is 0 meters per second, right? Because we're starting at rest. The time that is spent pushing equals 1.2 seconds, and the displacement is what we want to find out, displacement 1. Same thing for canoe 2, all right? We're just going to do that separately. So we have our acceleration right here. We have initial velocity and time. I think we have a kinematics equation that we can use to solve for that. Displacement, displacement, the x, sorry for that noise you probably hear, that's my dogs running around upstairs, equals initial velocity times time plus 1/2 acceleration times time squared. Okay, that's going to go away because the initial velocity is 0. And so we're going to have our displacement for canoe 1 is going to be 1/2 acceleration of 1, which is negative 0.31 meters per second squared, times the time squared, so that's 1.2 squared. All right, so that's going to be the amount that you might say canoe 1 displaces in is 1.2 seconds. So 0.5 times negative 0.31 times 1.2 squared is going to be negative 0.22 meters. All right, I'm going to dotted line box that because it's asking us for the total separation. So it's saying canoe 1 is going to move backwards that far. We've got to find out what canoe 2 moves, and then we'll just add them up. All right. So initial velocity for canoe 2 is going to be 0 meters per second as well. The time is 1.2 seconds. The displacement for canoe 2 is what we want to find out. All right, we have that acceleration right there, so we can say the displacement for canoe 2 is initial velocity times time. That, of course, is going to become 0 because initial velocity is 0, plus 1/2 acceleration of canoe 2 times time squared. All right, so the displacement is going to be 1/2 times the acceleration of canoe 2, which is 0.18 meters per second squared, times the time, which is 1.2 seconds, that value squared. All right, so the displacement for canoe 2 is going to be 0.5 times 0.18 times 1.2 squared. I get 0.13 meters. So if canoe 1 is displaced 0.13 meters, all right, and canoe 2 is displaced 0.22 meters in the opposite direction, and then total separation is really the sum of those two. All right, so what is that? 0.35 meters is there. You have to do that in a different color because it's not red nor green. It's the displacement or the separation between both of them. 0.35 meters is our total separation of the canoes after 2 meters. After 1.2 seconds. The second part really was just a kinematics equation, but this the point here is that we can tie kinematics into our discussion with forces because of that relationship to acceleration. All right, example 5.5, part B. Thanks for following along. I'll see you on the next one.